Hello. This live event is brought to you by Proceedings of the IEEE. Reconfigurable systems probably conjure a lot of visions up to the layperson, things like transformers. And that would be a type of physical reconfiguration. But what we're talking about is functional reconfiguration. So if we go to the next slide. The idea, and this is an example of a field programmable gate array, is that we start with a very sophisticated piece of silicon, but like a CD, it's blank until a user configures it. So we sort of depict this idea as functional reconfigurability. And it's about, in the case of the FPGA, a process that captures design and translates that into essentially a pattern that goes into silicon. And so this is all digital, the themes that we focused on in the special issues was how to take ideas like the FPGA and extend them into computing and RF and optical and even things like programmable matter, which we think is the sort of futuristic limit of reconfigurability. And I guess one of the first things you say, well, that's very neat, but why bother? I mean, so this reconfigurability seems like an interesting curio, but why have it? And I guess the first point is flexibility is very important, especially in the 21st century. It's an enabler like no other. The idea that I can take something inside of a system and send information into that system and have it fundamentally alter the functions of a system is a very powerful idea. This idea of I call it X on demand, means that we can develop systems much faster. A field programmable gate array is already built. We can program it as fast as we can think and turn those thought patterns into ones and zeros. Another powerful idea with reconfigurable systems is that we can reduce the inventory. So we can use one field programmable gate array or a small family of these to replace many parts. And so this allows us to collapse inventory and supply chain. We can do field updates. That's very important. Systems are very complicated, so even a production system will often have many defects and software faults that are only discovered much later. And if you build a custom integrated circuit, you are stuck with that pattern. FPGAs allow you to change those ones and zeros and change and often recover functions in the field. Another idea, which is a bit more abstract, it's not used as much, but I think it will be, is the idea of resiliency. The idea that if we find breaks in the system that we can recover from those faults by reprogramming. And in fact, we have seen evidence and demonstrations of self-healing behavior where we can recover functions when a system is damaged. And finally, the idea of adaptive or dynamic reconfigurability is very, very important concept. Okay. So I've talked about why reconfigurability. Let's talk a little bit about the nuts and bolts of what reconfigurability is. How do we implement it? And on this slide, we have shown that at the top we have very primitive elements. So we have to have these little building blocks of functions, like a programmable switch, which is like a software wire. Or on the right, a configurable resistance, which Art will talk about in a minute. Now we take those primitive elements, which are like the atomic building blocks, and create circuits, which is shown below. And we build programmable functions that way. And then at the bottom is this idea of a fabric. And a fabric is like a field programmable gate array, where we have an entire digital system that can be configured to implement other digital systems. So future reconfigurable systems are all about this kind of special way of doing virtualization, that I can have a blank substrate take on many different behaviors. At one level, it's virtual because we're using information to configure it, but it is implemented in real life in the functionality of the system.